Hi, I'm Mark Barsamian. In this video, I'll be giving an introduction to counting and probability. This material is from section 9.1 of the book. The corresponding homework is this collection of exercises from section 9.1. I'll be discussing random processes, sample spaces, and events, and I'll introduce the equally likely probability formula. I'll be discussing how we can describe sample spaces using set notation, but also using other kinds of illustrations. We'll do some basic examples, and I'll introduce the idea of choosing items with replacement versus choosing without replacement. And then we'll end the video with discussing the idea of counting the elements of a list. Start with the definition of a random process. To say that a process is random simply means that when it takes place, one outcome from some set of possible outcomes is sure to occur, and all of the possible outcomes in the set are equally likely to occur. The sample space, S, of a random process is the set of all possible outcomes. An event, E, is simply a subset of a sample space. And if a sample space S is a finite set, then every event E will also be a finite set. In this case, these symbols, n parentheses S and n parentheses E, can be used to denote the number of elements in the sample space S and in the event E. And in this case, the probability of E, denoted with this symbol, P parentheses E, is given by the equally likely probability formula. That's this. The probability of E is the number of elements in the event E divided by the number of elements in the sample space S. And again, remember that the event E is simply a set, and the sample space is simply a set. So we'll talk now a little bit about describing sample spaces and events using set notation. The first example is similar to a number of problems from the book. It involves flipping a coin 4 times. So a coin is flipped 4 times, and the value of each flip, that is H or T for heads or tails, is recorded. Question A is describe the sample space S using set notation. Then find n parentheses S, that is the number of elements in the sample space S. Well, this is fairly tedious, so I'll just dive right in. There's our sample space S. Notice that the number of elements in that set is 16. Notice that it's very tedious to write that out, and it's also very tedious to read. It's really hard to pay attention to all that chicken scratching. In question B, we define E to be the event that the number of heads is exactly 2. The question is to describe E using set notation, then find the number of elements in E and the probability of E. So there's our set E. Now you can see that there are 6 elements in E. So that means that the probability of E is 6/16. Let's go on. Question C is to illustrate the sample space S using a table. So this is getting at the idea that writing out the set roster is incredibly tedious and also not helpful for the reader. This is just not very easy to pay attention to. Now, illustrating the sample space using a table can be done a number of ways. So the idea is just to keep trying lots of different ways of illustrating sets, and you'll end up with a large repertoire of ways of illustrating sets. So here's one way. So there's a listing of all the outcomes in the sample space. Now let's go on. Question D is to illustrate the event E on the illustration of the sample space S that we did in question B. Well, let's go back up, and I'll grab a copy of this and copy it and put it down on the page below. We'll go down there and find it when we go back down. Okay, so there's the illustration of the sample space. Now our event E is the event that exactly two of the rows are heads. So let's just illustrate those with a little asterisk by each of those. So there are 6 rows that have exactly 2 heads in each row. Let's go on. Define F to be the event that the number of heads is at most 2. Illustrate F on the illustration of the sample space. Well, let's go back up and grab another copy of that same illustration. So I'll copy this and I'll move it down, and when we scroll back down, we'll find it there. So there's our illustration from before. And again, F is the event that the number of heads is at most 2. Well, at most 2 means that the number of heads could be none, or could be 1, or could be 2. The rows with the green asterisk are the event F, and now our job is to find the number of elements in the event F. It might be easiest to just count the number of rows that don't have an asterisk. There are 5 rows that don't have an asterisk. There are 16 rows altogether, so that must mean that there are 11 rows that do. So that means that the probability of F will be 11/16. Let's go on. When flipping a coin 4 times, what is the most likely number of heads? Explain using an illustration of the sample space. Well, we need to go up and get another copy of that illustration. So we'll copy this and put it back down on that page below, and when we scroll down, we'll find it. All right, there's our illustration. So we need to think about the number of heads and the number of rows that have that number of heads. So we've got, let's think about the number of rows that have exactly 2 heads. Let's put a little red 2 by the rows that have exactly 2 heads. And then let's put a green 3 by the rows that have exactly 3 heads. Let's put a black 4 by the row that has exactly 4 heads. And then let's put a blue 1 by all the rows that have exactly 1 head. And then let's put a black 0 by the row that has no heads. So the question is, what's the most likely number of heads? Well, realize that the probability of a certain number of heads is going to be the ratio of the number of rows that have that number of heads divided by 16. That's the total number of rows. So the question is, which of these numbers appears by the most rows? Well, the red number 2 does. We can actually do this in great detail, though. We can actually figure out the probability of all of them. We see that when flipping a coin 4 times, the most likely number of heads is 2. Okay, let's go on. Now let's discuss drawing a card from a standard deck. So a card is drawn from an ordinary deck of 52 cards, and the suit and denomination are recorded. The suit, of course, is spades, clubs, hearts, or diamonds. The denomination refers to the number on the card, or if it's a face card, the face on the card. Listing the sample space S using set notation is incredibly tedious. So tedious that you would not want to write it out by hand. There's the sample space in set notation created using typing with a computer. It's tedious to type even, and it's tedious to read. And even a table showing all the elements of the sample space is tedious to create and tedious to read. But it is possible to illustrate the sample space using a hand-drawn table that does not take so much time to draw, and that's still useful. So question A is to illustrate the sample space using a table with row and column headings, but empty cells, and then find the number of items in the sample space. So there's an illustration of the sample space that didn't take quite so long to draw, and it's also useful visually. Now clearly we can see that the number of elements in the sample space is 52, because of course we have 52 cards, but also we have 4 rows with 13 columns in each row. Let's go on. Question B, define E to be the event that the chosen card is red and is not a face card. So the question is to illustrate event E using that illustration from the previous question. So we have to go up and copy that and bring it back down. So I'll copy this illustration and put it down on the next page, and then we'll scroll down and find it there. So there's the illustration, and we're supposed to illustrate E on this same illustration. So E is the event that the card that's drawn is red and is not a face card. Well, I'll illustrate this with red dots. There's a quick illustration of the set E. Now we're supposed to find NE and PE. So the number of elements in that set is 18, so the probability is 9/26. Let's go on. In question C, we define F to be the event that the denomination is at most 5, counting aces high. We're supposed to illustrate F on the illustration of the sample space from A, which I've brought down here already, and then find the number of elements in F and the probability of F. Well, the denomination being at most 5 means that denomination of 5 is allowed, but also any denomination less than 5. So I'll illustrate these with a green dot. So the number of elements in set F is 16, so the probability of F is 16/56, which is 2/7. Let's go on. Now let's talk about rolling a pair of dice. A pair of dice is rolled and the numbers are recorded. Each die is a cube with 6 sides. One of the die is blue and one of the die is red. As with the previous example involving drawing a card from a deck, the sample space can be listed in set notation, but it's very tedious to write and also very tedious to read. So if we could list the outcomes this way, we could have a pair of numbers. The blue number on the left is the number on the blue die. The red number on the right is the number on the red die. So that circled pair means that I rolled a 1 and a 4 on the blue and the red die, respectively. So again, that set roster is tedious to write and tedious to read. This table is a little bit clearer to read, but it's still tedious to write. Also, it's very cluttered. Remember in the previous example, there was an illustration of the sample space that was a table that I typed by computer. That's easy enough to read, but there's not much you can do with that table besides just look at it. It actually turned out to be more helpful to have this table for the sample space that consisted of empty cells for each element of the sample space, because those cells could be filled in to describe an event. Well, the same goes for this situation of rolling a pair of dice. We can illustrate the sample space using a hand-drawn table that doesn't take so long to draw and is also very useful. So I'm going to have the blue roll represented by a number down as the heading of each row, and the red roll represented by a red number that's the heading for each column. So there's the table. In this table, this cell represents rolling a 2 on the blue die and a 5 on the red die. Let's go on. But what if there are 3 or more dice? Then the sample space can't be so simply illustrated with a table of cells, but some kind of table representation of the sample space may still be possible and may be more helpful than the set notation representation. We encountered this in example 1 when we were discussing flipping a coin 4 times. Now let's go on. In example 3, I want to talk about rolling a die that has colored faces. So I have a single die. It has 6 faces. 2 of the faces are painted red, 2 are painted green, and 2 are painted blue. The die is rolled 3 times, and the colors that appear face up on each roll are recorded. For instance, this string, RGB, would denote that the colors that appeared face up on the first, second, and third roll were red, green, blue. List the elements of the sample space in a table, and then find the number of elements in the sample space. Well, here we're kind of at liberty to do whatever works, whatever is not tedious to write. So I'm going to try a different layout, see if this works. So there's our sample space. Notice that it's got 27 entries in it. Each string is one outcome. Let's go on. In question B, we're going to define E to be the event that all 3 rolls produce different colors. We're supposed to illustrate that on the illustration of the sample space from A, and then let's also list all the outcomes of the event in set notation, and then find the number of outcomes in that event and the probability of that event. So we have to go up and grab that illustration and bring it back down here. Okay, here we go. There's the event. I'm going to copy it and put it down below, and when we scroll down, we'll find it. All right, let's scroll down. There's the copy. So we have to illustrate event E, that all 3 rolls produce different colors. I'll circle each of the outcomes that is in event E. So we see that there are only 6 outcomes in event E. We can list them. We see that the probability of E is 6/27, or 2/9. Let's go on. Question C will define F to be the event that 2 of the colors that appear face up are the same. We should illustrate F on the illustration from A. Well, I've already copied that here. Then we should list all the outcomes in the event in set notation. So we have to find all the strings that have 2 of the colors that appear face up are the same. I will circle these in green. So there's event F. Now I'm actually not going to list those in set notation because it would be too tedious. But let's see if we can quickly count them. Notice that each column has 6 circled lines in it. So that means there are 18 outcomes in event F. So the probability of event F is 2/3. Let's go on. Now I want to talk about choosing multiple items with replacement versus without replacement. So example 4. An urn contains 2 red balls labeled R1 and R2, 2 green balls labeled G1 and G2, and 2 blue balls labeled B1 and B2. A ball is drawn from the urn and its color recorded, not its number, just its color. The ball is then put back into the urn. Now here's the idea of replacement. The ball is put back into the urn, and then a ball is again drawn from the urn and its color is recorded. Question A is to draw the sample space using a table and find NS. Well, even though all that's being recorded is the color of the balls, it's still going to be helpful to list all the balls with their names. So I'm going to list down as the row headings the ball that was drawn the first time. And then for my column headings, I'm going to label the second ball drawn. So there's our sample space. You see that it's a 6 by 6 table, so the number of elements in the sample space is 36. Let's go on. Question B is to define E to be the event that the 2 drawn balls are the same color, and illustrate E on the illustration of the sample space from A. So we need to go up and get that illustration and make a copy of it and bring it back down. We'll do that now. So I'm going to copy this sample space illustration and put a copy of it down below, and when we scroll down, we'll find it there. So we have to illustrate E on this diagram so the 2 drawn balls are the same color. I'm going to illustrate this event by putting a black dot in each cell that represents an element in set E. So there's my event E. This cell represents the outcome where the first time a ball was drawn, it was the green ball labeled G1, and that was the same ball that was drawn the second time. This outcome indicates that the first time a ball was drawn, it was B1, the blue ball labeled B1, and the second time a ball was drawn, it was another blue ball, but it was not B1 again, it was B2. So there's an illustration of event E. Now we have to find N of E and P of E. So we see that the probability of E is 1/3. Let's go on. In question C, we're going to define event F to be the event that the 2 drawn balls are not the same color. And we should illustrate F on the same illustration of the sample space from A, which I've copied and put down here. So there's our illustration of F. This represents the first ball drawn was G2, a green ball. The second ball drawn was R2, a red ball. So the only cells that are empty are these ones that were filled in the previous example, or the previous question. Now we have to find the number of elements in this event and the probability of this event. We see that the probability of event F is 2/3. Now, example 5, this is a variation on the previous example, but drawing without replacement. We have the same urn containing 2 red balls and 2 green balls and 2 blue balls. And again, we're going to draw a ball from the urn and just record its color. Now this time, the ball that we drew, we're not going to put back into the urn. That is no replacement. We're going to go on and draw a second ball from the urn and record its color. So this is the idea, again, of drawing without replacement. So question A is to draw the sample space S using a table and find NS. Well, I've put a copy of the table from the previous example. We're going to modify this table. Now, how do we do that? How will we modify this table? Well, since we're drawing the second ball without replacing the first ball, it's impossible to have this cell. We can't have ball R1 drawn twice. We can't have ball R2 drawn twice. You see that every entry in the diagonal is grayed out. So our sample space consists of the cells that are not grayed out. So what's the number? Well, it's the total number that we had minus the number of cells that we grayed out. Let's go on. Now in question B, we're going to define E to be the event that the two drawn balls are the same color, and we should illustrate that event on that same illustration and find the number of elements in that event and the probability of that event. So we need to go up and grab that illustration and bring a copy down here. So there's the illustration. I'll copy it and put it down below, and when we scroll down, we'll find it there. So here's the illustration that I've copied and brought down. Now we have to illustrate the event that the two drawn balls are the same color. Okay, so that's going to be the same dots that the same cells that we filled in the earlier example, like this, where we had the two drawn balls of the same color, but we don't get to put dots in the gray cells. So we see that the probability of E is 1/5. Let's go on. Question C, we're going to define F to be the event that the two drawn balls are not the same color. We have to illustrate F and find the number of elements in set F and the probability of F. We'll notice that the black dots are just like the black dots that we had in example C in question C of the previous example. That is, none of the black dots representing two drawn balls that are not the same color, none of those black dots fell on the diagonal. So we're unaffected by the diagonal having been grayed out. So our number of elements in set F is 24 again. Now let's compare this current example 5 to the previous example 4. In example 4, the probability of drawing two balls the same color was 1/3, and the probability of drawing two balls different color was 2/3. In the current example, with the diagonal grayed out, the probability of drawing two balls the same color has gone down. It's only 1/5 because we lost all those gray cells. Those are not available to us. The probability of drawing two balls of different colors went up. We don't have any more dots than we had in the previous example, but as a fraction of the total number of cells available, that number is larger now. Let's go on. The last topic for this video is counting the elements of a list. See, there's a typo here. This should be 4. So suppose you wanted to answer this question. What's the probability that a randomly chosen 4-digit integer is a multiple of 7? Well, the approach to a solution would be the following. You define this random process, that is to choose a 4-digit integer at random. Then the sample space S would be the set of all 4-digit integers. And we would have to find the number of elements in that sample space, that is the number of 4-digit integers. And then we would let E be the event that the randomly chosen, this should say 4-digit integer. The randomly chosen 4-digit integer is a multiple of 7. So we'd find the number of elements in that event, and then the probability of that event would be n of E divided by n of S. And notice that finding n of S and n of E would both involve counting the elements of a list. So that brings us to this idea of counting the elements of a list. Well, the book presents a theorem for use when counting lists. This Theorem 9.1.1, the number of elements in a list. It says this: if m and n are integers and m is less than or equal to n, then there are n minus m plus 1 integers from m to n inclusive. I think it's better to remember this as n minus the quantity m minus 1. But I strongly recommend not relying on that theorem. Rather, each time you need to count the elements of a list, I recommend that you show the list with an index for each item on the list, and then come up with your own formula for the number of items on the list. Figure out a way of presenting the calculation that's clear for you and for the reader. Once you're done, you can confirm your results match the result given by the theorem. Well, let's do that problem that was suggested. A 4-digit positive integer is chosen at random. Describe the sample space S using set notation. An ellipsis would be useful unless you want to write down a lot of numbers. So here's the sample space. So there's the sample space. Now, question B is to find the number of elements in the sample space and show the details of the calculation clearly. Here's where we're going to calculate the number of items in a list. Now, here's how I do this. The numbers that we want to count are the ones that are circled in green. We'd like to find out how many numbers are circled. I find it easiest to think this way. Think of the number of items in the whole list minus the items that you don't want. So then the counting is actually not so hard. Now that we've done that calculation, it's helpful to go back up and look at the theorem and see if what we did can be put in agreement with that theorem. The theorem says that we should get n minus m plus 1, or as I like to think of it, as n minus the quantity m minus 1. So m is our lowest integer that we're trying to keep, and n is the highest integer that we're trying to keep. So our m is 1000 and our n is 9999. So our calculation is n minus m minus 1. So it does work out to match the theorem. But again, I don't recommend starting with the theorem. I recommend starting with a list. Show clearly to yourself and to your reader what you're going to do to compute the number of items in your list. And then if you want to, at the end, show how that agrees with the theorem. Let's go on. Question C, let E be the event that the integer chosen is a multiple of 7. Describe E using set notation. Well, let's see. I'm not going to do that. I'm going to describe E using a list. So there's a list of numbers that are all multiples of 7. Now, we are interested in the event that an integer chosen is a multiple of 7. Remember that we're only choosing 4-digit integers. So that's this list. That's the list of integers that's our event. The list that starts with 1001, follows this pattern going by multiples of 7, and ends with a 9996. Question D, we're supposed to count the number of elements in that event. Well, we can count the number of items in this green set by counting the number of integers in this set. Now that green set is this large blue set minus this red set. So we get that the number of items in set E is 1286. Now, we can put this in agreement with the theorem. If we want to, we can let this number 143 be our m, and this number 1428 be our n. Then what we have here is n minus m minus 1. So that does agree with the theorem. Let's go on. Find the probability of E. Well, we see the probability of E is just 1286 divided by 9,000, which is roughly 0.143. Well, that's the end of this example, and that's the end of the video. Thank you.